In the previous video, we defined what a maximal ideal is, but we didn't talk about why maximal ideals are important in ring theory. And in this video, we're going to reveal that. So the coolest thing about maximal ideals by far is what happens when you quotient out by a maximal ideal. So here's a theorem, and we're going to prove this theorem in the video. So let's let R be a commutative ring with unity. And let I be an ideal of R. Okay? Then I claim I is a maximal ideal if and only if R mod I is a field. Yes, a field, as in commutative, and every non-zero element has a multiplicative inverse. Fields are really the most special rings we can work in. They're the nicest. They're the ones that behave the best. So this is a really interesting theorem if we can prove it. All right, so just as an aside, though, I just wanted to connect this to an example. So in a previous video, we talked about quotients of this ring, the polynomial ring on the real numbers. We tried taking the quotient of r bracket x by the ideal generated by x squared, and then also took the quotient of r bracket x by the principal ideal generated by x squared plus 1. And what's interesting about this is that we got two very different looking rings. We got one that was not even an integral domain, and then we got this one which I claimed was a field. And the reason it's a field is because it's isomorphic to the complex number field. All right, but now we can connect that to what's going on over here. What are we quotienting out by? What is the ideal we're quotienting by? Well, this one turned out not to be an integral domain. This quotient is not an integral domain and therefore has no chance of being a field because every field has to be an integral domain. So this theorem would claim that the ideal generated by x squared is not maximal. So this is not a maximal ideal. Okay, MXL, by the way, is a common abbreviation for maximal. And actually we can see that this is not a maximal ideal because, well, we can construct a bigger ideal that's not all of the polynomials over the reals and is strictly bigger than x squared. So we could say the ideal generated by x squared is a proper subset of the ideal generated by x, which is in turn a proper subset of r bracket x, and all those are ideals. Okay, how do we know that these are proper subsets? Well, we know that the polynomial x lives here, but does not live in this ideal because that ideal consists of only multiples of x squared. So that shows that that's a proper subset relationship. But also the polynomial 1 lives here in r bracket x but does not live in the ideal generated by x. So those are all proper ideal relationships, and that means this is not maximal. But on the other hand, this theorem would also claim that this ideal, the one generated by x squared plus 1, is maximal. And it's going to turn out that the reason for that has to do with the fact that x squared plus 1 is not reducible into smaller polynomial factors, smaller degree polynomials, over the reals. It is over the complex numbers, but not over the reals. We'll explore that in more detail later on, but for now, let's prove the theorem. All right, this is an if and only if, so as always, we're going to have two things to do. So let's start by assuming I is maximal, and we will show R mod I is a field. Okay, well, what would it mean to prove that R mod I is a field? That means that we need to show each non-zero, and I'm going to put non-zero in quotes for reasons I'll explain in just a minute, each non-zero element of R mod I has a multiplicative inverse. Now here's what I mean by non-zero. In R mod I, the zero element is this. It's not just zero, it's 0 plus I, it's that coset, or the congruence class of 0 mod I. So we just need to keep that in mind, that we don't just mean the zero element of the ring, we mean the 0 coset of I. Okay, but anyway, we need to show that each non-zero element has a multiplicative inverse. So suppose X is in R such that this element of R mod I is non-zero. Okay, well, for this to be non-zero, this means X is not congruent to 0 mod I. This means X is not an element of the ideal. Okay, it means X is not an element of the ideal because if X were an element of the ideal, then that would mean that X is congruent to 0 mod I. Okay, so we know X is not an element of the ideal. So we need to find some Y also in R mod I such that the class of X times the class of Y is equal to the class of the unity. Now, before I move on with the proof, I just want to do a little bit of thinking first. Just do a little bit of planning. Okay, what would it mean if we said that X times Y, or the class of X times the class of Y, is congruent to 1, or is the class of 1 mod I? Well, this would mean that XY is congruent to the unit, or the unity, mod I. So this would mean that XY plus some element of I is equal to 1. This is true for some A and I. So in other words, if I could find these objects, if I could find a Y and find an A in I, and Y can be anything in R, such that XY plus A is equal to unity, then I think I'd win. I think I'd be done. Okay, but why should that be possible? That's the tricky part. Why should I expect to be able to do that? Okay, so here's the secret. I know that I is maximal. So I know that I contains a lot of stuff. There's a lot that could go here. Not everything, because I is a proper ideal. That's what it means to be maximal. But it is maximal and contains a lot of the stuff in R. So the idea is, by adding multiples of X, I should be able to get 1. And the reason I can get 1 is actually I'm going to be able to get anything that I want here if I just take the ideal and tack on multiples of X. And in turn, the reason why that is true is because if I take I and tack on anything else and make a bigger ideal, I'm going to get to R. I'm going to get to the entire ring because I is maximal, and there is no ideal between a maximal ideal and the entire ring. So that's going to be the idea here. All right. So let's consider the ideal. I'm going to call this angle brackets I comma X. And I'm going to write down a definition of that because it's non-standard notation. So this is the set of all A plus XY such that A belongs to I and Y belongs to R. Okay, I claim this is an ideal. Okay, and I'm going to just do a quick walkthrough of how you prove it. I'm not going to write the proof here. It would actually make a great homework exercise. But why is this an ideal? Well, if I add together any two elements of this set, then I've got like some ideal element plus xy, and then some other ideal element plus x times some other y. I add those together and use the distributive property and the fact that ideals are closed under addition. Then I just get one big ideal element plus one big multiple of x. So this is going to be closed under addition, and then we need to show it absorbs multiplication, but that's not too much trouble either because I multiply this by anything in R. Like imagine multiplying all of this by R. Well, I get AR here, and that's still an I because I absorbs multiplication. And I still get a multiple of X here because multiplying by R doesn't shift this off of being a multiple of X. So this really is an ideal. It's the smallest ideal generated by I and X together. Okay, so this ideal, since X doesn't belong to I, this ideal is bigger than I, but it does strictly contain I. But contains I. Okay, and because this ideal is bigger than I, and I is maximal, so that means the ideal generated by I and X together has to be the entire ring. Got to be the entire ring because I was maximal. The only stop left is the entire ring. Okay, so that means unity in particular belongs to this ideal. Sorry, that should be I comma x. Unity belongs to that ideal. So unity is expressible as a plus xy for some a in the ideal I and some y belonging to R. And now we're just about there, because this means xy is congruent to 1 mod I. I mean, what we see right here is the exact definition of xy being congruent to 1 mod I. It's xy plus an element of I there. Okay, thus, semicolon, thus, the congruence class of x times the congruence class of y mod I is equal to the congruence class of 1. And therefore we have this thing in R mod I this is a multiplicative inverse of brackets x. In other words, the congruence class of y mod I is a multiplicative inverse of the congruence class of x. And because I was able to do that for every, again, quotation marks, non-zero x, such an inverse exists for each quotation marks non-zero x in R mod I. R mod I is a field. I'm glossing over the fact that fields need to be commutative, but R mod I is going to be commutative because R is commutative. Taking quotients doesn't stop things from being commutative. If anything, it will only make things better. Okay, so that is one half of the proof. Yes. Okay, that's fun. I love that argument. It's such a clever argument, and I'm sure that the first time I had to do it, I did not think of it on my own. I did this time, but only because there's a certain natural appeal to it. So anyway, let's do the other half of the argument now. Okay, let's just move down here, give ourselves some more room to work. There we go. Okay, so the other half of the argument is we assume that R mod I is a field, and we prove that the I has to be maximal. So let's assume R mod I is a field. We'll show I is maximal. Okay, so to do that, well, let's use the definition of maximal ideal to structure our proof. So suppose we have some other ideal J. So J is an ideal of R such that I is contained in J, which is contained in R. Okay, and to prove that I is maximal, I need to show that either J is equal to I or J is equal to R. Okay, and I think the way that would be the most fun would be to assume that J is more than I, because if J is just I, then we're done, right? So let's assume that J is not I, so it contains more than just what's in I. And we're going to prove that if that happens, then J is going to be forced into being the entire ring. All right, so that'll be the strategy. Let's assume J contains some X not in I. Okay, we'll show J is all of R. Now, here's where things are kind of tricky. I mean, how do I know that just containing some X not in the ideal I forces J to be the whole ring? Well, I'm assuming that R mod I is a field, so I'm probably going to need to use that idea at some point. I think this is a good time to switch over into thinking about the quotient ring. Okay, so let's go ahead and take this X here, which seems interesting. Let's move it over into the quotient ring. So consider this element of R mod I. Now, because X is not in I, we know the class of X is not the zero class modulo I. In other words, this is because X is not in I. Okay, great. So because that's true, well, why would we want to know that X is non-zero? It's because we know R mod I is a field, and therefore this X is going to have a multiplicative inverse. Has a multiplicative inverse, which we'll again call Y, or brackets Y. Okay, so then what does that mean? This means brackets x times brackets y is the class of the unity of R. And again, this is kind of like the work I was doing over here, where I was just translating all of this. Like I thought, well, what would that mean for x times y, or the classes of x and y, to have product class of 1? And I said, well, that means that xy is congruent to 1. And then I worked out a nice relationship between this thing that's happening in R mod I and this thing that's happening in just plain R. We're going to do the same thing here. Okay, so this means xy is congruent to unity mod I. And let's translate that. So this means xy plus a is equal to 1 for some a in I. Okay, but just a minute, just 1 minute here. We know that this belongs to J because x belongs to J. X is that element of J that wasn't in I, and then xy is just a multiple of x. And we know that this is in I, and I was also a subset of J. Okay, but think about what that means. This belongs to J, this belongs to J, therefore this belongs to J. And one thing you're going to get good at recognizing after you do a few of these proofs is that once an ideal contains 1, it's all over. That ideal has to be the entire ring. We'll show why here. Okay, so 1, which is xy plus a, this belongs to J. All right, since, and I'm going to make this explicit here, since x being in J implies xy being in J. Sorry, my pen is skipping like crazy. There we go. And a belonging to I also implies that a belongs to J. There we go. Now we have it in writing. All right. So 1 belongs to J, and thus for every, let's call it R, belonging to the ring, 1R, which is R, also has to belong to J because J absorbs multiplication. So since 1 belongs to J, every multiple of 1 belongs to J, but then you've just described every element of the ring. So J has to equal R. So if we deny that J is the ideal I, J is something bigger than I, then J ends up just having to be the entire ring. Therefore, I is maximal. Isn't that great? I don't know, I just think that is the coolest arguments. You don't have to agree with me, but I don't think you're going to be able to prove that I'm wrong. All right, so that's pretty cool. So now we know that modding out by a maximal ideal creates a field, and that's the only way that you can mod out and create a field. The only way you mod out and get a field is if your ideal that you modded out by was maximal, and that's